Hello friends, in continuation with the last lecture, today we are going to talk about the energy bands, how the energy bands are forming in case of the semiconductor. As we are much aware of the things that if suppose we are having the isolated atoms all together and they are having their own discrete energy states, quantized energy states will be there. Now suppose if these isolated atoms are brought together, okay, they are brought close together to form a solid. Okay, if I just collect the large number of the atoms together and try to form a solid, then obviously when we bring them together, there are various interactions occurs between the neighboring atoms. When they just try to come together, there is a plenty of the interactions happens uh, when they are coming together. So now what kind of the interactions happens? There might be the forces of the attraction as well as the repulsion. Not only the attractive forces will come into the picture, but also there will be the repulsion. After certain distances, the atoms will try to repel with each other, and what happens that to form a solid, they will find a balance or appropriate distance between them, and or what we can say, on the other hand, they will find a balance at a proper interatomic spacing to form on the crystal, or the for that particular crystal to form. So during this process, the important changes occur in the electronic energy uh, level configurations, and these changes result in the various electrical properties of the solid. So on which basis the electric properties of the materials are depend? When the atoms are coming close together, and there's many interactions to happen, and they find the appropriate balance in the interatomic distances, and obviously their energy levels, uh, or what we can say, the important changes occurs in the energy levels configurations, and they are actually responsible for the varied electrical properties of the that particular solid. Now let's try to look at the electronic configuration of solids. Let's consider the first example as, or a simple example is silicon, and look at its electronic configuration. What are the things are composed within it? Uh, yeah, this is what we can say the electronic configuration: 1s2, 2s2, 2p6, and uh, 3s2 and 3p2, something like that. There are two electrons within the first cell, then the in the next orbit will be having the eight electrons will be there, and then there will be the outermost shell will have composed of the eight electrons, and so on and so forth, right? So this is how it is composed of, and we can have the outer orbitals as well. For dotted lines is something different than the usual one. Okay, so now you can see the inner core is the nucleus containing the positive charge plus 14 in case of the silicon. Then the orbitals near to the nucleus are called as inner orbitals. Then the outermost orbitals are called as the valence orbitals. Okay, outermost orbitals are called as valence orbitals. Now, the electrons present in the inner orbitals are called as the core electrons. Core electrons, so electrons filled within it, completely filled electrons in that particular orbitals are called as core electrons. Then the electrons present in the outermost shell are called as the valence electrons. The if suppose we supply some amount of the energy over here, and we just try to excite these electrons in the outermost shell, so they will try to occupy in the they will try to get excited and occupy the upper energy states which is available for the conduction. So we can say the first shell after the valence orbital is called as the, or is called as the first excitation orbital, or orbit which is present next to the valence orbital is called as the first excitation orbital one. Okay, now let us focus on the outermost shell, that is n is equal to 3. Here there are two 3s electrons and three 2p electrons interact to form the four hybridized sp3 electrons when the atoms are brought close together. So what happens in case of this case is nothing but the Sp3 hybridization. There is one of the electron from the 3s state will be excited, and it will be occupying the 3p state, or else what we can say in the other hand, one of the electron from this 3s state will be occupying the px, py and pz. So pz 3pz position will be occupied by the electron which is excited from the 3s shell, and it will be having the almost equal energy states, and they are forming the hybridized energy shell, or hybridized energy electron states will be forming. We call it as a hybridization. Okay, so sp3 hybridization. Now the figure which is going to see in the moment later shows the Coulombic potential wells of the two atoms close to each other, along with the wave functions of the two electrons centered on the mm, two nuclei one. So if you just try to solve, if we know this Coulombic potential, so we can try to solve the Schrodinger equation for it, and try to find out the wave function corresponding to such interactions or such interacting system. So that the composite two electron wave functions is nothing but the linear combinations of the individual atomic orbital. Individual in the sense that two atoms which are interacting, their individual linear combination of the atomic orbitals we are going to see in this case, right? So this is what we can see over here, right? So now let's look at this. This is the one of the atoms wave function which is represented with the psi1, and the another atoms wave function is represented with the psi2. If we just try to, these are the atomic orbitals corresponding to it, right? So if we just try to bring these together, so their wave functions try to overlap with each other, their wave functions start to overlap with each other, and there will be the possibility that the we can have the anti-bonding state as well as the bonding state. Okay, anti-bonding state as well as the bonding state will be forming. This is the Coulombic potential for the individual. If there is a no second atom is present over here, then we will be having the such a kind of the potential is like a well over here, right? But because of this second atom which is present next to it, or about close to it, each other, because second atom will be having again the potential like this, but they are brought to close together, they start interacting with each other, and their potential becomes like this. So it's bend. So this is overlap point of the this two electrons functions. So now, this linear combination of atomic orbitals known as the LCAO, when the two atoms are brought together, leads to the two distinct normal modes. It will be having the two distinct normal modes. One of them is higher energy. Higher energy, obviously, there is anti-bonding states. So, whenever there is a bond formation, there is the minimum so system will be at the minimum energy level, or the its energy will be lower, total energy of that system will be lowered one. So it will be forming the bonding orbital one. So now the electron probability density is high in the region between the ion cores, that is the covalent bonds, leading to the lowering of the bonding energy level and the cohesion of the, so crystal will be formed in this case. So whenever there is a electron probability density is high within the region, so obviously that is the bond formation. See, now electron probability density is high, but the its energy is minimized at that time, so that will lead to the bonding state, or the formation of the crystal. If instead of the two atoms, one brings the large number of the atoms, and okay, I consider here the n atoms together, there will be the n distinct LCAO. So that means n number of the distinct or a different linear combination of the atomic orbitals will be there, and there will be n closely spaced energy levels in that particular band will be forming over there. So the fundamental particles in the nature, now when they are coming together, so the fundamental particles in the nature have either the integer spin or integer spin and called as the bosons. Like one of the example for the integer spin particle is photons. On the other hand, half integer spin are known and they must be have, there might be the possibility that they can have the half integer spin as well, and they are known as the fermions. One of the example is the electron, proton, neutron. So quantum mechanical wave functions uh, of the electron wave quantum mechanical wave function of the electron has two parts. One of the part is the spatial part, that is radial part, we can say the orbital part, that is r dependent x y z, and the other hand it will be having the another part is the spin dependent part, that is the spin half and spin minus half part. Okay, so it is composed of the both the parts, spatial as well as the spin dependent. So is a multiplication of each other. It can be shown that the fermions wave function of the multi-electron system must be the antisymmetric one. What is the requirement? That the fermionic wave functions of the multi-electron system must be the antisymmetric one. Okay, we require the antisymmetric wave function. So we know that this total wave function is composed of the spatial part as well as the spin dependent part. Okay, now there is a possibility that the one of the wave function can be the symmetric one, so other has to be the antisymmetric, then and then only the combination remains the antisymmetric one. So when the spatial part is the symmetric one, electron spin wave function must be antisymmetric, and vice versa. Means in the spatial part, if it is antisymmetric one, the electron spin function must be the uh, what we can say the symmetric one. Okay, to get the total wave function as to be anti-symmetric one. Hence the two electrons in the bonding orbitals have the opposite spin. So why, what is the reason behind to have the electrons in the bonding state have the or opposite spins? Is this one to get the total wave function has to be anti-symmetric one, and those in the anti-bonding states have the parallel spins, and this explains the Pauli's exclusion principle. Is a well-known thing in the case of the this physics. Okay, Pauli's exclusion uh, principle. Okay, to determine the energy levels of the bonding and the anti-bonding states, so it is important to recognize that the region between the two nuclei, the Coulombic potential phi of r is lowered one. Okay, it can be shown in the figure. It can be seen from the figure as well, and compared to the isolated atom, it's a dashed lines, right? So it is because of, it is because an electron here would be attracted by the two nuclei rather than the just one. So if suppose one of the electron is placed over means one of the atom is placed over here and one of another will be here, so the outermost electrons within this will be attracted by this atom as well as this another atom. So there are two cores nearby. It's that's why it is getting just attracted by the two nuclei, and its energy level gets lowered one. So the lowering of the energy of the bonding state that gives rise to the cohesion of the crystal. So that's why we get the cohesion of the crystal, or crystal is getting formed. So the lowest energy level correspond to the totally symmetric LCAO, the highest corresponds to the totally antisymmetric case, and the other combinations lead to the energy levels in between. That's, thank you.